In section 4.2, we are actually going to take a look at a few things that I've probably accidentally used even in my language already, words that I haven't actually defined, and we're going to give them some formal definition now so that we can really use them appropriately. We're going to start with taking a look at the two pieces of the title that we haven't really defined yet, prime and composite. So prime. A prime number is any positive integer with exactly two distinct positive divisors. Distinct means what? What's the word distinct mean? Different. In this context, yeah, it means different. So let me ask you a question. The number 1, is the number 1 prime? Does the number 1 have exactly two distinct positive divisors? What do you think? What are the divisors of the number 1? Just one, right? It doesn't have two distinct divisors. It only has one. So the number 1 is not prime. What's the smallest prime number? 2. So if we're looking at factors that are prime, 2 would be a prime factor, but 1 would not. It's a factor, it's just not a prime factor, okay? The number 1 is not prime. So 2's prime. Give me a couple more just for fun. 3, 5, 7, yep, 11, 13, 17, that's plenty. We'll stop there. Yeah, there's a lot of prime numbers, right? But the category that has to be satisfied, or the description that has to be satisfied, is that whatever the number is, it has 2 and only 2 different factors to make it up. Itself and 1. Doesn't divide by anything else. So a composite number is not something that's not prime. It has a distinctly different description than that. It may not feel that different, but I'll tell you why in a minute. It's any positive integer with more than 2 distinct positive divisors. Is the number 1 composite? No. It doesn't have more than 2. It has less than, right? So the number 1 is not prime and it is not composite. So you don't get to categorize every number as one or the other. But after we pass the number 1, all the rest of them we can. Okay? Every other number beyond 1, whole numbers, beyond 1, is one or the other. It's either prime or it's composite. All right, factorization is any expression of a number in factored form. Okay, so I keep coming across this phrase, and I'm kind of avoiding it as I work with my intermediate algebra and my college algebra students, and I keep using the words breaking down. But the real mathematical word that I'm wanting to sort of avoid as I'm talking to them, because I just don't want them to get confused on me, because sometimes their eyes glaze over. Do your eyes ever glaze over when people use too much vocabulary? It happens to me in other areas too, not in math, but in other areas where it's just an overload. I use the phrase breaking down, okay? Factorization is a breaking down of a number into smaller components. That's what it really is. And then prime factorization is specifically breaking the number down into prime factors. So in essence, you keep breaking the number down until you can't do anything else. You're left with all primes. And remember, 1's not a prime, so as long as we get down to the smallest thing before we would get to a 1, then we're done. Prime factorization. And we definitely need some examples. Yeah. So let's take a look. Kind of big number wants us to find the prime factorization for each of the following, and I am going to show you 2 ways of doing this. We already talked about factor trees, just like I think I said the word once, the phrase once in the last section. And we're going to start there with factor trees. Sometimes it's very easy to find a particular factor, sometimes it's not. This number, I think, very nicely, we would probably recognize it divides by 0, or by 10, because of the 0 at the end, right? So it's a pretty good place to start, 10. Here's 2,366. I will break the 10 down. 2 5s. 2 and a 5. Sorry, didn't say that quite right. Your turn. What are you going to do with 2,366? You could split it in half. At the very least, you know it divides by 2. Why? Because it ends in a 6. Okay, so at the very least, even if you don't know what else to do, you know you can divide it by 2. If you divide it by 2, what do you get? Nice. Calculator is going to be your friend in this chapter. Please, bring it if you haven't been. 1183 is not super friendly. It's not even. And it doesn't divide by 3. I mean, very quickly you can add that together and you don't get something that's a multiple of 3. It's not by 5 because it doesn't end in a 5 or a 0. So our next prime number would be what Sally just said, which was a 7. So if we're just going up our list of prime numbers, which we wrote down over here, the first several of them, right? 7 would be the next one to try. And the calculator, thankfully, without having to do it by hand, tells us it works. What is our other factor there, Sally? 169. 169. And you may recognize that one. Does anybody recognize 169? 13. It's 13 squared. And if you don't, you would do the same thing, right? You know it's not divisible by 2, by 3, by 5. You could try the 7 again. It's not going to work. You could try 11. Eventually you get to 13, and it's 13 times 13. So this would be the supporting work. And then your answer would be to make sure you include all of these digits that are the prime factors at the end. This is sort of the drawback of this particular method, is that, well, part of it's a drawback. It depends on how neat and tidy your work is, as to how neat and tidy your trees probably are. But at some point, your trees you might just accidentally forget one of the branches, and that would end up giving you an incorrect solution. I've circled all of them. So our prime factorization here would be 2 times 2, which is 2 squared, times 5, times 7, times 13 times 13, or 13 squared. How could I check to make sure this is right? Yeah, there's 2 things. First of all, you need to be able to look at all these numbers and say 2, 5, 7, 13, yes, they're all prime. Are they? Yes. And then, Hannah's right, we could multiply them back out, and the calculator is our friend to do that, right? Plug them all into the calculator, make sure that when I multiply them, I get 23,660. Okay, so factor trees are one way to do this. They're great. You can use factor trees, but I do want to show you one additional way. And I'm kind of partial to this just because it organizes the information in a little bit more compact form, okay? So I kind of liken, well, I'll say that in a minute. Let me show you this form and then I'll liken it. 23,660. And the first thing I'm going to do is just to divide by the smallest prime number that it divides by, which would be a 2. And again, our calculator's our friend. If I divide this by 2, I'm going to do the division going downwards because there's not going to be any remainders. No remainders to be had here. What is 23,660 divided by 2? 11,830. And then I would divide by, again, the smallest prime number that divides this number, which would be 2. And if I do that, what do I get? Nice, 5,915. Does this also divide by 2? No, so I don't try 2's anymore. I'm done. 2 is over and done with. 3 would be the next place to stop. Will this one divide by 3? It doesn't. You can either try it or you can use your rule where you add the digits up. What's the next number that you would try? 5. Is it going to work? Yes. Yeah, because it ends in 5. So what is 5,915 divided by 5? Okay, now we've seen that 1,183 before, so we kind of already know where this is heading because we've gotten a number to repeat now from the other method. We know this doesn't divide by 5. I don't even need to test 3 and 2, not even trying, because I already did, and it didn't work in an earlier part of the problem. So 5 now doesn't work, so I would try 7, and we know 7 works because we already saw that happen a minute ago. Gives me 169, divides by 13, 13. So the nice thing, and the reason I like this so much, is because my answer's all right there. It's just all in a row. Not only that, but it's grouped together. Notice the 2's are both right beside each other, and the 13's are beside each other. It's more structured. We all think differently, so I don't have a problem if you look at this and you're like, yeah, that's not for me. That's fine. It doesn't have to be. Obviously, I get the same answer, right? 2 squared times 5 times 7 times 13 squared. This feels to me like when I was in high school and I was learning ways of doing brainstorming with writing. And one of the brainstorming ways was to make these bubbles, and my ideas are all in these bubbles, and then I attach bubbles together and these kind of things. I don't even know what it was called, but I remember these bubbles. And then another way of doing the brainstorming was to doing an outline. So I liken the factor tree to my bubble thinking, and this division algorithm thing going on here on the right-hand side to outlining. And I think like the outline, that's how my brain works. And so to me, it's very appealing, and I like to cling to that one. But it's also good just for you to know, because you're going to have people who think both ways if you end up teaching this material to students, right? Yeah, you are. So a couple options for thinking about that. Now, we're going to shift gears slightly. The directions are the same, but the problem looks quite different. This problem is not one single digit number, like not single digit, but one filled out number, simplified number. It's got some exponents to it already, correct? Okay. So when I'm looking at this, remember the reason I told you that you knew you were sort of done right here was because all of them were primes raised to powers. But that's not what you have here, right? 16, 81, 6, actually none of them are prime. So we're going to take each one of them individually, and we're going to find out what the prime is. So if I took 16 and I broke it down, I'll do this one with a factor tree. What would be 16? Break down. 4 and 4. So it factors into 4 and 4, and each of the 4s factor into 2's. So I can rewrite 16 as 2 to the 4th, but notice there was already a 4th on the 16, so this is 2 to the 4th to the 4th. One of the 4ths was already there. The 4th came when you factored 16. Let's do 81. I'll do 81 with my division tree. Smallest prime number that divides 81. It's a 3, because 8 plus 1 is 9. Okay. What is 81 divided by 3? 27. Smallest prime that divides 27? 3, giving me a 9, and then 9 is also 3 times 3. So this ends up being 3 to the 4th, again to the next 4th, because it's 81 to the 4th. And then you have 6, and I think you can do 6 without a tree. What is the factorization, prime factorization for 6? 2 times 3, you bet. Now, the 2 times 3 to the 6th does look different than the other two pieces. But all of the pieces that we now have fit into some rules that we've seen for properties, or some properties we've seen for exponents back in chapter 3. When I have an exponent raised to the exponent like this, what do I do with those exponents? You multiply. Good job. So this would be 2 to the 16th. And it's the same one for the next piece, right? 3 to the 16th. Now the last piece, 2 times 3 to the 6th, isn't the same rule, right? I don't have an exponent to an exponent. What do I do to simplify that expression? I would have a distribution kind of a process going on, right? So like 2 to the 6th and 3 to the 6th. Everybody good so far? Because these all have exponents, if you left the dots out in between them, you'd probably be okay, but I'll go ahead and keep my dots in there just for now. All right, so 2 times 3 times 2 times 3, those are my bases. Those are all prime, but is there any other way to simplify what's here?
Add the exponents.
All right. The 2's here have the same base, 2, right? One of them has an exponent 16 and the other has an exponent 6. And Hannah, what did you say I could do with them? I can add the exponents. Do you remember that property? So this could become 2 to the what? 22nd. And interestingly enough, the 3's are the same, right? 16 and 6, so also to the 22nd. This would be the prime factorization for this number. We're going to do one more, and then we're going to stop for today. What about this one looks different than the last one? something super important that makes it different. The addition in it makes it different. That's actually the most important problem. There's addition here. So when I look at that addition there, what it means is I'm going to have to factor this differently. In particular, the two pieces that I underlined are completely independent of one another, added together. But do they have anything that divides both of them? So let's start with the 2's. How many 2's are in the first addend? 2. How many 2's are in the second addend? 4. So both of them have at least 2 2's, right? Let's start there. I'm just going to write that down. They have a 2 squared in common. How many 3's do they have in common? 4. The first one has 5, the second one has 4, so they have 4 3's in common. And how many 7's do they have in common? All 55 of them, right? I would strongly encourage you not to multiply this out. Your calculator can't handle it, actually. It'll turn things into scientific notation. It's too big. It'll give you that capital E notation. You're right. All right, so what did I do, actually? Well, I sort of did something, and this is what really factoring is I divided, okay? So when I pulled the 2 squared out right here, I divided it out of that term, and it's just not there anymore. But when I divided it out of the next term, what happens when I have 3 to the 5th and I take out 3 to the 4th? There's still a 3 left. So the 3 remains. No more 2's, took them both out. But I only took out 4 3's, there's still a 3 left. What about the 7 to the 55? Yeah, that's already gone too, right? I pulled those completely out. So this addition comes in right here still. The next piece, it's 2 to the 4th. Did I pull them all out? No. What do I have left? I still have 2 2's left, so I have 2 squared left. How about the 3 to the 4th? Pulled all those out. 7 to the 55? I pulled all those out. Let's just suppose for an instant that I pulled it all out. Let's say all of this got pulled out in front. What would be left? No, let's say like I had a problem where I pulled 2 to the 4th out, I pulled 3 to the 4th out, and I pulled 7 to the 55 out. What would be left? It's division, remember? 1, right? You're dividing. When you pull them out like this is division. So if I divided by the exact same expression I already had, I'd get 1. It's a really common mistake for people to just ignore that piece and it just disappears pretending like it's a 0. If you factor everything of something out, you're left with a factor of 1. All right, so let's see what happens on this one. What is 3 plus 2 squared? 3 plus 4, which is 7. Okay. Anything else you notice then? Right. I already have a 7, so this will be 2 squared, 3 to the 4th. Sorry, my dots keep getting lost. They aren't super crucial, but 7 to the 56th. Because there was already 7 to the 55.